Now, it says that the student claims that the concentration of the weak acid has a higher concentration in the flask when the pH of the titration mixture is equal to 4.00, and they said because the pH is less than 7. Do you agree or disagree with the student's claim? Justify your answer. Well, if you remember some of the essential knowledge statements for topic 8.7, then you know that we should be comparing the pH of the solution with the pKa value. Welcome to AP Chemistry Review and Practice. My name is Michael Farabaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this lesson, I'll give you the chance to review and practice topics 8.6 to 8.8. As you can see on this slide, these topics fall under Unit 8 in the AP Chemistry curriculum, Acids and Bases. You can add your comments and questions below this video, and you can also email me with your comments and questions at apchemistryreviewandpractice@gmail.com. Check out the links in the video description area, which include the link to the packet that accompanies this video. Now let's move on to the review for topic 8.6, Molecular Structure of Acids and Bases. Here are some essential knowledge statements from the AP Chemistry course and exam description. The protons on a molecule that will participate in acid-base reactions and the relative strength of these protons can be inferred from the molecular structure. Strong acids, such as HCl, HBr, HI, HClO4, H2SO4, and HNO3, have very weak conjugate bases that are stabilized by electronegativity, inductive effects, resonance, or some combination thereof. Carboxylic acids are one common class of weak acid. Strong bases, such as group 1 and 2 hydroxides, have very weak conjugate acids. Common weak bases include nitrogenous bases, such as ammonia, as well as carboxylate ions. Electronegative elements tend to stabilize the conjugate base relative to the conjugate acid, and so increase acid strength. Now let's move on to the practice for topic 8.6. This is question 1. In question 1, we see two equations, and it says the ionization of two different acids are represented by equations 1 and 2 shown above. Which of the following identifies the acid that has the larger Ka value and provides the correct justification? Now, if we look at the 4 answer choices and we focus on that justification column, we can see a common feature. Since each justification involves the phrase stabilizing the conjugate base, let's explore that structural feature of the conjugate base. So we have two conjugate bases which appear on the right side of the equation. We have the ClO- ion, which is known as the hypochlorite ion, and then we have the BrO- ion, which is known as the hypobromite ion. So obviously the only difference between these two structures is chlorine versus bromine. And one of the essential knowledge statements for topic 8.6 says that electronegative elements tend to stabilize the conjugate base relative to the conjugate acid, and so increase acid strength. So do you remember your trends in electronegativity? Let's see which atom, chlorine or bromine, is more electronegative. So electronegativity generally tends to decrease from top to bottom. So there's chlorine and bromine. We can see that chlorine is more electronegative than bromine. And so if chlorine is more electronegative than bromine, then in terms of stabilizing the conjugate base, Chlorine does a better job of drawing electron density toward itself, and this helps to stabilize the negative charge on the oxygen atom in the conjugate base ClO-. And the more stable the conjugate base is, the more likely the equilibrium for the ionization of the acid will favor the formation of the products. So that makes HOCl, or hypochlorous acid, the stronger acid. And if HOCl is the stronger acid, we would expect HOCl to have a larger Ka value. So now we have all the information we need to answer question 1. So the larger Ka value is for HOCl. That means that the correct answer to question 1 is either A or C, but it's because of that chlorine atom that is more effective at stabilizing the conjugate base ClO-, so that makes the correct answer to question 1 choice A. All right, well now let's take a look at question 2, and we can see a table with 3 different acids that are labeled acid 1, acid 2, and acid 3. And so question 2 says the following. Information about 3 different acids is shown in the table above, and part A says which substance, acid 1 or acid 2, is the stronger acid. Justify your answer in terms of the pH of a 0.0010 molar solution of each acid. Now, if you've already studied how pH works, you know that the lower the pH value is, the higher the concentration of the hydronium ion in solution, but I will go ahead and do those calculations just to be sure. So if we're trying to figure out the concentration of the hydronium ions, and we know the pH, the concentration of the hydronium ions are going to equal 10 to the minus whatever that pH value is. So for acid 1, that 0.0010 molar solution of that acid, the concentration of the hydronium ion is equal to 10 to the minus 3, and you can see that the concentration of the hydronium ion is 0.0010 molar, so that's a pretty strong acid, acid 1. Now if we compare that with acid 2, now it's going to be that the concentration of the hydronium ion is equal to 10 to the minus 3.11. And when we do that math, we get a slightly smaller value for the concentration of the hydronium ion. It's actually 0.00078 molar. So the higher the concentration of the hydronium ion, the stronger the acid is. So here is my answer to part A of question 2. Each solution has the same concentration of the acid, HA, and acid 1, with a pH of 3, has a lower pH than acid 2, which is 3.11. So therefore, the acid 1 solution has a higher concentration of hydronium ions. Acid 1 is the stronger acid. Now, before we take a look at part B of question 2, I'd like to show you the difference in the structural features of acid 1 versus acid 2 that explain why acid 1 is the stronger acid. So it has to do with the number of fluorine atoms in each molecule. So if you can see that acid 1 has 3 fluorine atoms, whereas acid 2 has only 1 fluorine atom, that is the structural difference that explains why acid 1 is the stronger acid. So there are 3 fluorine atoms in the acid 1 molecule, and they do a better job at pulling electron density away from the oxygen atom in the conjugate base, as compared to only 1 fluorine atom in the acid 2 molecule. So this makes the conjugate base of acid 1 more stable, and this explains why acid 1 is the stronger acid. As we move on to part B, we're going to be comparing fluorine in acid 2 with iodine in acid 3. Let's go ahead and take a look at part B. So in part B it says, do you predict that acid 3 is a stronger acid or a weaker acid than acid 2? Justify your prediction in terms of each of the following: the relative electronegativity values of fluorine and iodine, and the relative stability of the conjugate bases of acids 2 and 3. So which atom, fluorine or iodine, is more electronegative? Remember that electronegativity tends to decrease from top to bottom down a group, so we can see that fluorine is more electronegative than iodine. And since fluorine is more electronegative than iodine, then that means that the fluorine does a better job at drawing electron density toward itself. This helps to stabilize the negative charge on the oxygen atom and the conjugate base. And so looking at this comparison of the two conjugate bases of acid 2 and acid 3, we can see that the conjugate base of acid 2 is more stable than the conjugate base of acid 3. So that makes acid 2 the stronger acid and acid 3 the weaker acid. So in part B, it said, do you predict that acid 3 is a stronger acid or a weaker acid than acid 2? And the answer is that acid 3 is a weaker acid than acid 2. All right, well, let's go ahead and take a look at question 3. And question 3 involves circling a hydrogen atom. So question 3 says that the reaction between hydrochloric acid, which has the formula C3H6O3, and sodium hydroxide, NaOH, is represented in the balanced equation shown above. And the Lewis diagram of hydrochloric acid is shown in the following diagram. Circle the hydrogen atom that most readily participates in the chemical reaction with sodium hydroxide. Now, on this next slide, this is from my video from my AP Chemistry CED Units playlist, where I was talking about topic 8.6, and we are looking at the fact that carboxylic acids are one common class of weak acid. The general formula of a carboxylic acid is shown above, where the letter R refers to a group of atoms bonded to the CO2H portion of the molecule. Now let's go back and take a look at hydrochloric acid. So right there, I'm highlighting on this slide, that is the carboxylic acid portion of the hydrochloric acid molecule. And so we have to circle the hydrogen atom that most readily participates in the chemical reaction with sodium hydroxide, and it's right there on the left side of that molecule, that structural formula. So this is the hydrogen atom that should be circled in question 3. I also wanted to mention to you that in a recent, it was actually 2024, AP Chemistry free response question, it was pretty much the same question. It says that the structural formula of something called lactic acid is shown, and students had to circle the hydrogen atom that most readily participates in the chemical reaction with sodium hydroxide. So the official scoring guidelines for this particular question from the 2024 AP Chemistry exam is right there, that the hydrogen atom that is part of that carboxylic acid group should be circled, so you should be familiar with what a carboxylic acid structural formula looks like. All right, now let's go ahead and take a look at the next question in this packet. This is question 4. In question 4, it says, the structural formula of methylamine, a weak base, is shown above. Which of the following best represents the structural formula of the conjugate acid of methylamine? Now, highlighted on this slide are two essential knowledge statements from topic 8.6. We've already seen in question 3 in this packet that carboxylic acids are one common class of weak acid that you should be familiar with for the AP Chemistry exam. But this other essential knowledge statement is relevant to question 4. It says that common weak bases include nitrogenous bases such as ammonia. So this is the structural formula of ammonia, which is NH3. It contains a nitrogen atom, so it's a nitrogenous base, and there's a lone pair of electrons on the nitrogen atom, and that lone pair of electrons behaves as a proton acceptor. So with a nearby water molecule, the lone pair of electrons accepts the proton from water, and it also forms the hydroxide ion. So we can see the hydroxide ion and the ammonium ion, which is NH4+. So the ammonium ion is the conjugate acid of ammonia. Now let me switch ammonia with methylamine, and you will see a very similar structure. So here is methylamine. Again, there's the lone pair of electrons on that nitrogen atom. It reaches out with a nearby water molecule and acts as a proton acceptor. So we get the hydroxide ion, and then we get the methyl ammonium ion. So in question 4, you are looking for the correct structural formula of the methyl ammonium ion, and hopefully you can see that that makes choice B the correct answer to question 4. All right, now it's time to move on to the review for topic 8.7, pH and pKa. Here are the essential knowledge statements from the AP Chemistry course and exam description. The protonation state of an acid or base, that is, the relative concentrations of the weak acid, HA, and the conjugate base, A-, can be predicted by comparing the pH of a solution to the pKa of the acid in that solution. So here are two possible choices. Now, when solution pH is less than the acid pKa, then the acid form, or the HA, has a higher concentration than the base form, A-. On the other hand, when the solution pH is greater than the acid pKa, now the base form, or A-, has a higher concentration than the acid form, or HA. And if you're wondering, what if the pH is equal to the pKa? Well, that was actually mentioned in topic 8.5 from a previous episode of AP Chemistry Review and Practice. So if you were doing a titration, then at some point when you are halfway to the equivalence point of the titration, which is known as the half equivalence point, then you will have equal concentrations of the weak acid HA and the conjugate base A-. And so pH equals pKa at the half equivalence point. But again, in topic 8.7, we either have pH is less than pKa, in which the acid form has the higher concentration, or pH is greater than the pKa, in which the base form has the higher concentration. Now, there's a couple of statements about acid-base indicators. So acid-base indicators are substances that exhibit different properties, such as color, in their protonated versus deprotonated state, making that property respond to the pH of a solution. And so to ensure accurate results in a titration experiment, acid-base indicators should be selected that have a pKa value that is close to the pH of the solution at the equivalence point. And I will show you an example of questions in this lesson where you can predict the appropriate acid-base indicator for a titration. All right, let's go ahead and move on to the practice for topic 8.7. This is question 5. Question 5 says that salicylic acid, which has the chemical formula HC7H5O3, ionizes in aqueous solution according to the equation shown above. In part A, it says that the Ka for salicylic acid is 1.1 times 10 to the negative 3. Calculate the value of pKa for salicylic acid. So, according to the equation sheet, we can see that the pKa is equal to the negative log of the Ka value. So if we take the negative log of 1.1 times 10 to the negative 3, then we get that the pKa value is 2.96. And now that we know the value of pKa for salicylic acid, then we are able to make a comparison between the pH of the solution and the pKa value for salicylic acid. It says that a student titrates a sample of salicylic acid with 0.010 molar sodium hydroxide using a probe to monitor the pH of the solution. The student is asked to predict which of the following substances has a higher concentration in the flask when the pH of the titration mixture is 4.00. So we can see on the left HC7H5O3, so that is the weak acid, or HA, and then on the right we can see C7H5O3-, and that is the conjugate base, or A-. Now, it says that the student claims that the concentration of the weak acid has a higher concentration in the flask when the pH of the titration mixture is equal to 4.00, and they said because the pH is less than 7. Do you agree or disagree with the student's claim? Justify your answer. Well, if you remember some of the essential knowledge statements for topic 8.7, then you know that we should be comparing the pH of the solution with the pKa value. So we need to compare the pH of the titration mixture, which is 4.00, with the pKa of salicylic acid, which we calculated in part A, and that's 2.96. So obviously 4.00 is greater than 2.96. And since the pH of the titration mixture is greater than the pKa, which species has a higher concentration in the flask? Remember that when solution pH is greater than the acid pKa, then the base form, or the A-, has a higher concentration than the acid form HA. So now we can decide, do we agree or disagree with the student's claim? So what I said for part B is the following. I disagree with the student's claim because the pH of the titration mixture, which is 4, is greater than the value of pKa, or 2.96, for salicylic acid. So therefore it is the conjugate base, the C7H5O3-, that should have a higher concentration in the flask. All right, well now let's go ahead and take a look at question 6, and you can see that the intent of question 6 is to choose the best indicator for a titration. It says a sample of base is titrated with 0.10 molar HCl, and the results are shown in the graph above. Based on the pH range of the color change given for each indicator, which of the following indicators would be the best choice for the titration? So let's focus our attention on the location of the equivalence point in this titration curve, which is going to be that rapid change in pH that occurs after a volume of 15 milliliters of the hydrochloric acid, or the titrant, has been added. So I will highlight that on the graph. So right there, that would be a pH range for that equivalence point of the titration that seems to fall approximately between pH 4 and pH 6. Now, that's when we want the pH indicator to change color. So if the pH of the titration mixture at the equivalence point for this titration is in this range, which is approximately between 4 and 6, we should choose the best choice for the indicator is the one that experiences a color change during the equivalence point of the titration. So which of these indicators would change color between approximately pH 4 and 6? Well, that makes methyl red the best answer for question 6. Now, I did a little research and I tried to find the pKa value for methyl red, and what I found was the following. The pKa value for this acid-base indicator, or methyl red, is approximately 5. So the pKa value of methyl red is 5.1. And when choosing the best indicator for a titration experiment, you want the pKa value of the indicator to be very close to the pH of the titration mixture at the equivalence point of the titration. Normally, the pH range, or the color change, is roughly plus or minus 1 on either side of that pKa value of the indicator. So since the pKa of methyl red is approximately 5, then the range of color change is roughly between pH 4 and 6. So you may recall that essential knowledge statement for topic 8.7: to ensure accurate results in a titration experiment, acid-base indicators should be selected that have a pKa value that is close to the pH of the solution at the equivalence point. So if methyl red has a pKa value of approximately 5, then there on the titration curve you can see that the pH of the titration mixture at the equivalence point is approximately pH 5. All right, well, hopefully you can see why that is the correct answer to question 6, choice B, methyl red. Now, let's go ahead and take a look at question 7. Question 7 says that trimethylamine, which happens to be another example of a nitrogenous base, it contains a nitrogen atom. It is a weak base that ionizes an aqueous solution according to the equation shown above. And in part A, it says that the Kb value for trimethylamine is 6.5 times 10 to the negative 5. Calculate each of the following for the conjugate acid, which has the chemical formula CH3 times 3, and then NH+. So you'll see that's the conjugate acid, which is located on the right side of that equation shown above. So what is the Ka value for the conjugate acid? Do you remember the relationship between Ka for an acid and Kb for its conjugate base? You can find it on the equation sheet. So it's right there, that the Kw, which has a value of 1.0 times 10 to the negative 14, is equal to the product of Ka times Kb for that conjugate acid-base pair. So if we know the Kb and we're trying to find the Ka, then we can do the following setup for the calculation. Kw, so 1 times 10 to the negative 14, divided by the Kb will give us the value of Ka for the conjugate acid. So it's going to be 1 times 10 to the negative 14 divided by the Kb, which is 6.5 times 10 to the negative 5. So when we do that math, we get that the Ka value for the trimethylammonium ion works out to be 1.5 times 10 to the negative 10. So that's the first part of what we needed to calculate in part A. Now, we're not quite done with part A. Now we have to find the pKa value for the conjugate acid, the trimethylammonium ion. But we have the Ka value, so all we have to do is take the negative log of the Ka to get the pKa value. So what is the negative log of 1.5 times 10 to the negative 10? Well, that works out to be 9.82. And so now that we know the pKa value for this conjugate acid, the trimethylammonium ion, then we are prepared to do a comparison between the pH of the solution and the pKa value for this acid. So let's go ahead and move on to part B of question 7. It says a sample of strong acid is slowly added to a solution of trimethylamine. The pH of the solution is measured during this experiment, and on the number scale below, circle each pH for which more than 50% of the trimethylamine molecules, again that's the weak base, are in the protonated form. So to produce the conjugate acid, the trimethylammonium ion, CH3 times 3NH+. Justify your answer. So how do we attack part B of question 7? This question is similar to the situation that we examined in question 5, part B. At which pH values would the conjugate acid, or the protonated form, CH3 times 3NH3+, the conjugate acid, have a higher concentration than the conjugate base? So under what conditions would the acid form have a higher concentration? Well, as you can see, that would be when the solution pH is less than the pKa. So when pH is less than pKa, then the acid form has a higher concentration than the base form. Let's figure out which pH values should we circle. We're looking for a pH that is less than pKa. So if the pH is less than the pKa, then the conjugate acid has a higher concentration than the conjugate base. So in part B of question 7, we should circle the pH values that are less than 9.82. So that would be pH 1 all the way to pH 9. Those are the pH values that should be circled. Okay, now it is time to move on to question 8 in the packet. And we can see in question 8, it's another example of choose the best indicator for a titration experiment. So question 8 says the following. A 10 milliliter sample of an unknown monoprotic acid, HA, is titrated with 0.10 molar sodium hydroxide. The reaction represented by the equation above occurs during the titration. The pH of the titration mixture is monitored, and the following titration curve is produced. Now, the same titration is to be performed again, this time using an indicator. And the following acid-base indicators are available in the laboratory. So we have bromocresol green indicator with a pKa of 4.9, and we have phenolphthalein indicator with a pKa of 9.4. So part A of question 8 says, on the titration curve in the graph above, draw a dot to indicate the pKa value for both bromocresol green, 4.9, and phenolphthalein, 9.4. So for bromocresol green, I will put a dot on the titration curve, which is located at 4.9, so right about here. And for the phenolphthalein indicator, I will put a dot on the titration curve, which is right about 9.4, or right there. Hopefully you can see that we are shooting for the equivalence point, not the half equivalence point, but the equivalence point. So just a reminder, which indicator, bromocresol green or phenolphthalein, is the better choice, it's based on that essential knowledge statement that I had mentioned earlier in this lesson. To ensure accurate results in a titration experiment, acid-base indicators should be selected that have a pKa value that is close to the pH of the solution at the equivalence point. So the correct answer to part B of question 8 is phenolphthalein. Phenolphthalein is the better choice to use in this titration experiment because the pKa of phenolphthalein, 9.4, is close to the pH of the solution at the equivalence point. Okay, now it's time to take a look at question 9, and question 9 says the following. The reaction between hypochlorous acid, which has the chemical formula HOCl, and water is represented by the equation above. A buffer solution is prepared by combining solutions of sodium hypochlorite, or NaOCl, and hypochlorous acid, HOCl. And the pH of the buffer solution is determined to be 7.82. Part A says calculate the molarity of the hydronium ion, H3O+, in the buffer solution. Remember that if we know the pH, then the concentration of the hydronium ion is equal to 10 to the minus whatever that pH value is. So the answer to part A is the concentration of the hydronium ion is equal to 10 to the minus 7.82. And when we do that math, we get 1.5 times 10 to the negative 8 moles per liter for the molarity of the hydronium ion in this buffer solution. Now, we will need that particular value as we move on to part B of question 9. So in part B, it says, calculate the value of the ratio. And the ratio is concentration of ClO-, or the conjugate base, divided by the concentration of HOCl, the weak acid, hypochlorous acid. So if you're not sure how to start the strategy for part B, let's see if we can write the Ka expression for hypochlorous acid. So if I look on the equation sheet, here is the generic form of the Ka expression for a weak acid. I can see concentration of the hydronium ion times concentration of A-, or the conjugate base, divided by concentration of the weak acid, or HA. Let's go ahead and write the Ka expression for hypochlorous acid. Now, when we do that, we get concentration of the hydronium ion times concentration of the conjugate base, or ClO-, divided by concentration of the weak acid, or HOCl. And you will notice that that ratio exists in the Ka expression if we only knew the concentration of the hydronium ion. Well, we do. That was our answer to part A of question 9. So what I'm going to do now is I'm going to substitute 1.5 times 10 to the negative 8 for the concentration of the hydronium ion into this Ka expression. And remember that 3.0 times 10 to the negative 8, that is the Ka, and that was given to us in this problem. So all I have to do is a very simple little algebra to solve for this ratio in part B. I'm simply going to divide both sides of this equation by 1.5 times 10 to the negative 8, and I will have the ratio that I'm looking for. So when I do that math, I get that the ratio of concentration of ClO- over concentration of HOCl is equal to what is essentially 3.0 divided by 1.5, because they have the same power of 10 to the negative 8. And so I get a ratio of 2. That's a very simple answer, but that is my answer to part B. And now we are ready to answer part C, since we have already answered part B. So it says in part C, based on your answer to part B, which substance, the HOCl or the ClO- has a higher concentration in the buffer solution? Well, since this ratio is greater than 1, that means that the concentration of ClO- should have the higher concentration. So this is what I said for part C. The ClO- has a higher concentration in the buffer solution because the ratio, concentration of ClO- over concentration of HOCl, is a 2-to-1 ratio. So ClO- has the higher concentration. All right, well, there are the answers to all parts of question 9. Now it's time to move on to the review for our next topic, This is topic 8.8, Properties of Buffers. Here is an essential knowledge statement from the AP Chemistry course and exam description. A buffer solution contains a large concentration of both members in a conjugate acid-base pair. The conjugate acid reacts with added base, and the conjugate base reacts with added acid. And these reactions are responsible for the ability of a buffer to stabilize pH. Now it's time to move on to the practice for topic 8.8. This is question 10. Question 10 says the following. Pyridine, which has the chemical formula C5H5N, reacts with water according to the equation shown above. So we can see that pyridine is an example of a base. It's actually a nitrogenous base. It contains a nitrogen atom. A buffer solution is prepared that contains equimolar amounts of the weak base, pyridine, C5H5N, and its conjugate acid, the pyridinium ion, C5H5NH+. And when a small amount of potassium hydroxide, which is a strong base, is added to this buffer solution, the pH of the solution changes from 5.23 to 5.25. Which of the following equations represents the reaction that accounts for the fact that the pH does not change significantly when potassium hydroxide is added to the buffer solution? So in topic 8.8, we know that a buffer solution contains a large concentration of both members of a conjugate acid-base pair. Now, for example, suppose that the buffer solution components are HA, representing a weak acid, and A- representing the weak base, the conjugate base. Now, suppose that we have this buffer solution. Which component of this buffer solution will react or be consumed when a small amount of a strong acid is added? Well, since HA is a weak acid, then that would not react with a strong acid, so the A-, or the conjugate base, would react with the strong acid. I will show the hydronium ion as a source of the hydronium ions would come from a strong acid, and it would produce HA, the weak acid, and water. So we can see that when we have a buffer, one component of the buffer is consumed, and then the other component of the buffer is produced, but the ratio will stay relatively constant, which is why the pH doesn't change very much when either a strong acid or a strong base is added to the buffer. Now, suppose that a strong base is added to this buffer solution. Well, then the HA would react with the strong base in the form of the hydroxide ion, and it would produce A-, the conjugate base, and water. So again, we can see that one component of the buffer is consumed, and then the other component of the buffer is produced, but that ratio stays relatively constant, and the pH does not change very much. So again, to summarize, you have either a strong acid added, and the conjugate base would react, or you have a strong base added, and the conjugate acid would react. Now, what if we have something like ammonia, which the general formula of ammonia, a weak base, can be represented as capital B? Well, in that case, the B, or the base, would react with the strong acid to produce Hb+, the conjugate acid, or if you have a strong base, then the Hb+ would react with the hydroxide to produce B. But either way, the two components of this conjugate acid-base pair in the buffer, they would stay relatively constant in terms of their ratio, and that would keep the pH from changing. Now, back to this particular question. So pyridine would be like that capital B in the slide that I just showed you. And so we have the weak base, capital B, and then we have the conjugate acid Hb+. Well, let's remember that a small amount of a strong base, potassium hydroxide, was added as described here in question 10. So what we're looking for is the hydroxide ion reacting with the conjugate acid, or the Hb+, to produce the conjugate base and water. So if I put that equation and I line it up with the four choices in question 10, hopefully you can see that we're looking for the pyridinium ion, the conjugate acid, reacting with hydroxide to produce the other member of that buffer solution, and that would be the pyridine. So the correct answer to question 10 is choice A. the pyridinium ion would react with the strong base, the hydroxide ion, to produce some molecules of pyridine, its conjugate base. Now, as we move from question 10 to question 11, we're going to see a similar set of equations that we have to consider. So let's go ahead and take a look at question 11. In question 11, it says the following. Hydrofluoric acid, which is a weak acid, HF, reacts with water according to the equation shown above. A buffer solution is prepared that contains equimolar amounts of HF and F-. Now, instead of adding a strong base like we saw in question 10, here a small amount of a strong acid, nitric acid, HNO3, is added to this buffer solution, and the pH of the solution changes from 3.17 to 3.15. Which of the following equations represents the reaction that accounts for the fact that the pH does not change significantly when the strong acid, nitric acid, is added? So there's the weak acid, HA or HF. There's the conjugate base, F- or A-, and so we're adding a small amount of a strong acid. So it's going to be this equation, that the conjugate base, A-, reacts with the strong acid to produce the conjugate acid, HA. So I'm going to go ahead and write this equation, and let's line this up among the four choices in question 11. So A- plus the hydronium ion to produce HA in water. That's very similar to choice B. So when a small amount of a strong acid was added to this buffer, it was the F- ion that reacts with the hydronium ion to produce HF in water. So the message that I'm sending you from questions 10 and 11 is, once you know the two components of a buffer solution and you know whether a strong base or a strong acid was added to the buffer, then you can choose the appropriate component of that buffer solution to react, and then it will produce the other partner or the other component of that buffer solution. All right, now that we are done with questions 10 and 11 in this packet, let's move on to question 12, also involving a buffer solution. In question 12, it says the following. A chemist measures the pH of a solution in a beaker that contains equimolar amounts of HNO2, nitrous acid, which is a weak acid, and its conjugate base, the nitrite ion, NO2-. Now, the pH is recorded as 3.40, and then the chemist adds a small amount of solution X to the beaker and stirs the mixture thoroughly. Now, the identity of solution X is either a strong acid, HCl, or a strong base, NaOH. And the particulate diagrams shown below represent the relative amounts of the HNO2 and the NO2- present in the solution in the beaker before and after solution X is added. Note that water molecules and ions, such as Na plus or Cl minus, are omitted from the diagram. So let's start with the particulate diagram before a small amount of solution X is added to the beaker. So if I count the HNO2 particles in the diagram on the left, I see 1, 2, 3, 4, 5 particles of HNO2, and then I can see 5 particles of NO2-. So we have an equimolar amount of HNO2 and NO2-. So that pH is 3.40. Now, here comes a small amount of solution X. This is going to cause a change in the amounts of HNO2 and NO2-. And so based on this change, we will know whether solution X was a strong acid or a strong base. So the addition of solution X will change the ratio of NO2- to HNO2, and this change in the composition of the solution will reveal whether solution X is a strong acid, HCl, or a strong base, NaOH. Let's count the particles in the diagram on the left and see what has changed. So there's the HNO2. I see 1, 2, 3, 4, 5, 6. So it looks like the amount of HNO2 in this beaker has increased, and the particles of NO2- have decreased from 5 to 4. So now we know what's going on here. As a result of adding solution X, the concentration of the weak acid, HNO2, increased, and the concentration of the conjugate base, NO2-, decreased. So we know that a strong acid must have been added to this buffer solution. Why? Because if we add a strong acid, the concentration of the NO2- would decrease, and the concentration of the HNO2 would increase, so that's what happened. Now let's consider the four choices in this question. So I can see that HCl, the strong acid, is the correct answer, so the choices are either A or B, but when you add a strong acid, we would expect the pH to decrease. So the pH of the mixture at the end of the experiment after adding a strong acid would not be greater than 3.40, it would be slightly less than 3.40. So the answer to this question is choice A. All right, we have one more question in this packet. Let's go ahead and take a look at question 13. A student wants to prepare a buffer solution starting with a 1 molar solution of acetic acid, which has the chemical formula HC2H3O2, and the pKa value of acetic acid is 4.74. Now, the student also has access to a solution of 1 molar potassium acetate. So acetate is the conjugate base of acetic acid. And the question asks, how many milliliters of 1 molar potassium acetate must be added to a sample of 75 milliliters of 1 molar acetic acid in order to prepare a buffer solution with a pH of 4.74. So remember that when pH equals pKa, we have an equimolar amount of both the weak acid and the conjugate base. So if this buffer solution has a pH of 4.74, then pH equals pKa. So we need this solution to be the following. Concentration of acetic acid is equal to the concentration of the acetate ion. Now, in my video from my YouTube playlist organized by AP Chemistry CED units for topic 8.8, I had presented the following information. There are 4 possible combinations that should result in the formation of a buffer solution. And the substances that are combined are either the weak acid HA and the conjugate base A-, the weak acid HA and a strong base, hydroxide, a weak base represented as capital B and its conjugate acid HB+, or finally the weak base B and a strong acid, hydronium. So let's say we combine HA and A-. As long as the ratio of moles is approximately 1:1, then we have a good buffer in which HA and A- are present in equal amounts. But here's another way to make a good buffer. It's basically a half titration to get to the half equivalence point. So if you have HA and then you add hydroxide so that the number of moles of hydroxide is half the number of moles of HA, then that will also result in a good buffer solution with roughly equal amounts of HA and A-. There's a similar situation if you start with a weak base. You could combine the weak base with its conjugate acid in equal amounts to get a mixture of B and HB+. So for example, ammonia and ammonium, NH3 and NH4+. But you could also take that weak base and react it with a strong acid to get to the half equivalence point. So if you added a strong acid such that the moles of strong acid are half the number of moles of the weak base, then you would also produce a good buffer solution with a equimolar mixture of B, the base, and HB+, the conjugate acid. So this is what we're looking for in this part of the question. One method of creating a good buffer is to combine equimolar quantities of HA and A-. So what does that mean for this particular question? Well, if you have 75 milliliters of 1 molar acetic acid, then we would want to combine that 75 milliliters of 1 molar acetic acid with the same number of moles of the conjugate base. So I would need 75 milliliters of 1 molar potassium acetate. So that is what I'm looking for in part A of the question. How many milliliters of 1 molar potassium acetate must be added to 75 milliliters of 1 molar acetic acid? I want the same number of moles, so 75 milliliters of 1 molar potassium acetate should be added to 75 milliliter sample of 1 molar acetic acid, because this will create a solution in which concentration of acetic acid is equal to concentration of the acetate, the conjugate base, and pH equals pKa, or 4.74. Now, that half titration method that I had mentioned as another way to make a good buffer, that's coming up in part C of this question. But first we have to write a net ionic equation. So in part B, write the net ionic equation for the reaction between the weak acid, acetic acid, and a strong base, potassium hydroxide. So when I see potassium hydroxide, I know that that is really just the hydroxide ion that will appear in the net ionic equation. So strong base, weak acid, so it's going to be strong base reacting with weak acid, so HA, the weak acid, reacting with hydroxide, the strong base, to produce A minus, the conjugate base, and water. So I'm going to go ahead and write that generic form of the equation directly underneath my answer to part B. So HA would be acetic acid, HC2H3O2. Hydroxide, OH minus. And then I get the conjugate base, or A minus, that would be C2H3O2 minus plus water. So that is the reaction that would occur, the net ionic equation for the reaction between the weak acid, acetic acid, and the strong base, potassium hydroxide. So potassium is a spectator ion that was not included in this net ionic equation. Now, that half titration method is coming up in part C. So part C says how many milliliters of 1 molar potassium hydroxide, the strong base, must be added to a sample of 100 milliliters of 1 molar acetic acid in order to prepare a buffer solution with a pH of 4.74. Justify your answer. So we're not going to add enough hydroxide to go all the way to the equivalence point. We're going to add enough hydroxide to get to the half equivalence point. So another method of creating a good buffer is to take a sample of the weak acid, or HA, and then get it to the half equivalence point. So what does that mean? You add half the number of moles of hydroxide as compared to the number of moles of the weak acid, HA. So if I have 100 milliliters of 1 molar acetic acid, I don't want to add 100 milliliters of the strong base. I want to add 50 milliliters of the strong base. So what I said for part C is the following. If we take 50 milliliters of 1 molar potassium hydroxide, the strong base, and we add that to 100 milliliters of the 1 molar acetic acid, then this will result in a chemical reaction, so an acid-base reaction, which you can see represented by the answer to part B, in which half of the moles of acetic acid are converted into the acetate ions. And so if we do that, then the final solution will have equimolar amounts of the weak acid and its conjugate base, and then pH equals pKa, 4.74. So the half titration method is another good way to make a good buffer. Now you can see all of the answers to question 13 in the packet. This was the last question in this packet. So now we have come to the part of the lesson where I give you advice to help you avoid common mistakes. So my first piece of advice is if you need more information for topics 8.6 all the way to 8.11, check out the YouTube video, which comes from my YouTube playlist organized by AP Chemistry CED units, and you can find that link in the video description area. My next piece of advice, read the question carefully and make sure you are answering the question that is being asked. Always show your work for your calculations, and as I mentioned in terms of topic 8.6 and carboxylic acids, the general structure of a carboxylic acid is shown below. And if the AP Chemistry exam asks you to circle the hydrogen atom that participates in a reaction with a base, or the hydrogen atom that is lost when the acid donates H+, then you should circle the hydrogen atom shown in the following diagram. Something I would like to mention, this came from the 2025 AP Chemistry exam. And this question is related to the structure of the carboxylate ion. The carboxylate ion is the conjugate base of a carboxylic acid. So what you can see is this question from the 2025 AP Chemistry exam. The student had to circle the atom that not donates the proton, but rather accepts the proton. So we're looking at the conjugate base, C2H3O3-, and so you can see the correct answer was to circle the oxygen atom located on the right side of that structure. And as you can see on this slide, that there were actually two possible answers because each of those oxygen atoms is equivalent because of resonance. So I just wanted you to see a recent AP Chemistry exam question involving carboxylic acids. In this case, it was the carboxylate ion, which is the conjugate base of a carboxylic acid. All right, my next piece of advice is there's an inverse relationship between the Ka for an acid and the Kb for its conjugate base. And structural features such as resonance or the presence of an electronegative atom or atoms can help to stabilize the conjugate base of the acid. The more stable the conjugate base is, smaller Kb, the stronger the acid is, larger Ka. And my next piece of advice is that ammonia, NH3, is an example of a weak base. Molecules known as amines, so for example, methylamine, CH3NH2, which we saw earlier in this lesson, these are examples of weak bases. So when amines behave as H+ or proton acceptors, the lone pair of electrons on the nitrogen atom accepts H+, forming the conjugate acid. My next piece of advice is that when choosing an acid-base indicator for a titration experiment, the color change should occur when the titration is at the equivalence point. Therefore, you should choose an indicator whose pKa value is close to the pH of the titration mixture at the equivalence point. Now here is some advice about buffers. A good buffer solution contains approximately equimolar amounts of a weak acid, Ha, and its conjugate base, A-, or a weak base, B, and its conjugate acid, Hb+. And there are 4 different ways to prepare a buffer. You could mix equimolar amounts of the weak acid Ha and its conjugate base, A-. You could mix equimolar amounts of a weak base, B, and its conjugate acid, Hb+. You could mix the weak acid with a strong base, hydroxide, so that the moles of hydroxide is half the number of moles of the weak acid. Again, the so-called half equivalence point method. You could do a similar thing with a weak base. You could mix a weak base, B, with a strong acid, H+, so that the moles of the strong acid are half the number of moles of the weak base. Again, the half equivalence point method. Also, we have seen net ionic equations in this lesson, so practice writing the net ionic equations for various acid-base reactions, and these were mentioned in topic 8.4 and featured in an earlier episode of AP Chemistry Review and Practice. Now here, on this slide, you can see that I'm focusing on the pH versus pKa, and I'm focusing on this region of an acid-base titration curve. So at point A on this titration curve, before the half equivalence point of this titration, the pH is less than the pKa, and the number of molecules of Ha are greater than the number of ions of the conjugate base, A-. Then at the half equivalence point of the titration, pH equals pKa, and the number of molecules of Ha are the same as the number of ions of the conjugate base, A-. And if you get past the half equivalence point in the titration, now the pH is greater than the pKa, so now the number of molecules of Ha is less than the number of ions of the conjugate base, A-. What I'm going to do on the next slide is show you what happens if, instead of starting with a weak acid and titrating with a strong base, as shown in this titration curve, what if we start with a weak base and we titrate with a strong acid? Well, we still have the point before the half equivalence point, at the half equivalence point, and past the half equivalence point. But notice how, unlike the previous diagram where it was going pH is less, pH is equal, pH is greater than the pKa, now you can see it's sloping in the other direction. So before the half equivalence point in this titration, the pH is greater than the pKa. So we have more B than Hb+. Now I'm at the half equivalence point of this titration. The pH equals the pKa, and the molecules of B are the same as the ions of the conjugate acid Hb+. And then it continues. Now the pH is less than the pKa. So we have more particles of Hb+ than we have the weak base B. So you can see how that works. Again, pH versus pKa is an important concept for you to know for the AP Chemistry exam. And I'm going to summarize buffer solution and reaction. So here we have a buffer solution that contains equimolar amounts of a weak acid and its conjugate base. Suppose that a small amount of a strong acid is added to the buffer solution. The pH would decrease slightly, the concentration of the acid would increase a little bit, the concentration of the conjugate base would decrease a little bit, and there you can see the net ionic equation for what happens when a strong acid is added to the buffer solution. Well, what if a strong base is added to this buffer solution? Well, then the pH would increase slightly. The concentration of the weak acid would decrease a little bit. The concentration of the conjugate base would increase a little bit. And again, you can see the net ionic equation for what happens when a strong base is added to the buffer solution. So you should be able to write the net ionic equation for what happens when either a strong acid or a strong base is added to a buffer solution. Here's a few more examples. So a small amount of a strong acid is added to this buffer solution. pH decreases slightly. In this case, the ammonia decreases and the ammonium increases. There's the net ionic equation. And what if a small amount of a strong base was added to this buffer? The pH would increase slightly. The concentration of ammonia would increase a little bit. Concentration of ammonium would decrease a little bit. Again, you should be very familiar with the net ionic equations for what happens when either a strong acid or a strong base is added to a buffer solution. Okay, well, now we have come to the end of this lesson. In my next lesson, I'll give you the chance to review and practice topics 8.9 to 8.11. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. Check out the links in the video description area, which include the link to my YouTube playlist organized by AP Chemistry units. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Thank you for letting me be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Keep studying, and I'll see you next time on AP Chemistry Review and Practice.